Hi everyone, we are the team of Rahul, Rohan, and Josue, and for our project we dealt with the hydrology of streamflow forecasting with deep learning methods. So the main motivation for our project was to improve upon the physical process-based hydrological models by utilizing the large data sets available, and by doing so we want to improve the flood forecasting in this era of climate change. So the conventional physical models of hydrology are usually heuristic and they are calibrated to one single basin and so non-generalizable. Whereas data-driven methods are end-to-end, they are trained on more data sets or basins, and with that, they are more generalizable and have been shown to be more efficient as well. The data set we used was called the Catchment Attributes and Meteorology for Large Sample Studies, or CAMELS for short. It's a publicly available data set with 671 basins across the United States, as shown in the figure. We divided the data sets into the training set and development set, as shown in the slide. And the input features were divided into two types. The first one is the time series hydrometeorological features that changes with time, like solar radiation, air temperature, precipitation, etc. And the other type is the time-independent static features of the basin, which is like the soil type, the slope, the snow fraction, etc. And the output obviously is the daily volumetric streamflow, like I mentioned before. So the proposed RNN model for our project was something we call the adapted GRU. The main difference between the conventional GRU and our adapted GRU is that it's adapted to take in two input features, the dynamic and static features I explained before, and they are trained on separate parameters. So that's how it's different from the conventional GRU. The baseline model we used to compare was called the Entity-Aware LSTM by Kretzert et al. 2019. We used their Git repository as our baseline to build our model upon. So this is a typical output of our AGRU model after hyperparameter tuning for a particular basin. The top one is on the depth set, the bottom one is on the train set. The blue lines are the ground truth values and the orange lines are the predicted values. As you can see, our model can learn the long-term hydrological dependencies of streamflow. So these are some statistical evaluation of the result. On the left, we can see that on the dev set, AGRU is able to perform comparably to the EA-LSTM. The different AGRUs on the x-axis are simply a different combination of hyperparameters. And with this evaluation, we were able to select some good hyperparameter combinations, and we were able to find that it is able to optimize on fewer epochs compared to EA-LSTM, and beyond that, it only overfits. The main takeaway is that the AGRU is a simple architecture and it converges on fewer epochs, so it is less computationally expensive and is within pretty good margin of the NSE score of EA-LSTM. And there is a much room for improvement, and it could potentially surpass EA-LSTM with more hyperparameter tuning. So this is all we have for this project. We would like to thank the teaching team for a wonderful quarter. Thank you.